Okay, so let's get started. So we're going to talk about today about social learning. So what do we actually mean by that? It is about changing of person's opinion or behavior based on observations. So based on observations of what you see, what other people do, right? Whether it is imitating the behavior of other people, or maybe changing your opinion based on the opinion of other people. So in some sense, this social learning setting is trying to model, for example, behavior of a committee, right? When you have a bunch of people who are deciding on a certain topics or a certain subject, and they have different opinions, and they start discussing it, right? And you can hear the opinion of another person, and then you can change your opinion based on that person's opinion, okay? So it is about influence, and it's about how within the group settings, the group could possibly reach a consensus, and consensus means the same opinion, right? Starting at the different points. Well, for example, you can think of committee deciding whether, I don't know, during your thesis defense, right? There is a committee deciding what grade to give you, and there are different possibilities from 10 to 4, right, or from 4 to 10 or whatever, and then each person has his own opinion, and then depending on other people's opinion, you can actually try to reach. The committee tries to reach a consensus, and that's the grade you're going to get. Right? And in this type of settings, it is very important who listens to whom, right? And sort of what is the weight of different people in the settings, right? So somebody who is more important, maybe people will listen to him more carefully. Okay? So that's sort of the setup. Now, of course, it's it's in more of a business settings. It can be like discussion in the boardrooms, etc., etc. But the idea is that there is some. Oh, and it also could be that the situation when there is some information available to some people, but not available to others, and this is also kind of the way the information would spread in terms of opinions. And so there is no centralized mechanism there. And the way networks plays in here is because when you think about, again, committee settings or discussion, when you try to reach an opinion, you're not listening to everybody, right? You're listening to very particular people because, you trust them, you respect them, whatever reason is, but it's not usually that, you will be affected by everybody's opinion. There will be certain sort of opinion leaders for you who will affect your opinion, okay? And so then you can model this through network. So this particular lecture is based on the paper by Maurice Deroute, Reaching Consensus. Again, consensus is this mutual agreement with a group of people having an opinion, and the question is, can a common opinion or belief, could it be reached, right, in general, if it's possible? Another question, how long would it take? And, how each individual person will contribute to this, right? So again, the point here is that the opinion of the group is not necessarily just the sort of the average, the sum or average of your opinions. It is much more complicated process where opinion of every person can change based on opinion of the people the person is listening to, right? And it's not necessarily every person in the room. So this is a model. We're just going to start with the model right away. Let's think about this as, it's opinion on some subject, right? Whatever it is. Let's say if the person is going to pass exam or not, are we going to hire him or not? Are we going to, acquire this company or not? And let's say the opinion goes from 0 to 1 in the sense that 1 is, you're 100% for it, right? 50%, 0.5, you're sort of not sure, right? The close to 0, you're against this. And so every person has an initial opinion on the subject. And then what we're going to do is we're going to introduce what's called this weight on the opinion of others. So you can hear other people's opinion, and depending on this weight, that's how important that opinion, that person's opinion for you. All right? Now, it is I to j, so it is the way it is, the way it was set up in original paper. It's sort of a little bit inverse to what we used to do, but it's I to j. It means how much I listens to opinion of j. So it is, if it is 1, 3, so it is the first person, how much it listens to the opinion of third person. And then we just introduce an opinion update, very, very simple opinion update that will happen the following way. So the opinion of this person at step t plus 1 is equal to the sum of the opinions of the people in the previous step, but not all the people, but only those who he is listened to, and those opinions are weighted with this weight. All right? So, if you're listening more to one particular person, his opinion will be more important for you. Right? And so the question is, if we continue this type of iterations, very simple iterations, right? You literally just take opinion and add them up, opinions of other people, add them up with appropriate weight. If you keep doing this, if we're going to converge to the same opinion across the room. So what that means is for every I, this value P sub I for every I will be the same. So you start with different opinions. After several iterations, it could become the same. So the question is what are the conditions when this happens, and can this happen, and if it happens, how long it takes, and of course what value this is going to be. All right. So let me give you an example that will make this setup much more clear. So 3 people, right? And this network shows the way the people listen to the different opinions. Say the person number 1, he has sort of 1/3 he's listening to himself. Well, in some sense, okay, well, this is my confidence, right? If I'm 100% listening to myself and nobody else, well, of course, I don't give a shit about anybody else's opinion. But if it is 1/3, it means, okay, I'm 1/3 kind of staying, with my own opinion, but I'm also listening to this guy and to this guy. Okay? And I'm putting the weight 1/3 and 1/3 on their opinions. Guy number 2, well, he's more confident. He is 1/2 of his, sort of his own opinion that matters, and he listens to guy number 1. This person, he is even more confident, so it's like 3/4 of his opinion comes from himself, right? But then he kind of a little bit listens to what this guy thinks. Okay? So then this matrix of opinions, that's the way it's going to be. That's the way it's going to look like. And now, let's just sort of simulate the situation. Let's say initial beliefs about some certain subject were 1, 0, 0, right? So it is this person, for example, was completely for, right? And this against and against. Or, again, you can think about any sort of interpretation of this. So that's the initial opinion distribution, right? 1, 0, 0. Or like, for example, they decide how much money give to a particular business plan. I don't know, how much to fund it. All right, this says, fund it fully, and this says no funding. What committee will finally decide. So, the first iteration, just take this matrix, multiply by it. So what it really happens is you're saying, okay, I want to understand this. The result will be the opinion for the first guy, the opinion for the second guy, the opinion for the third guy. So the opinion for the first guy now will be his original opinion and the opinions of 2 other people added up with the weights, the way he is listening to them, right? And so after the first iteration, that's going to be the distribution of opinions, right? So they shifted. It was like this, now it's like this. So the first guy kind of reduced his confidence in the subject. The second guy increased his confidence in the subject. The third kind of ignored it. Well, the reason is because the way it happens, it only listens to this one, right? And in the previous iteration, they were both against. But this one changed his opinion because he also listens to this guy. And this guy had strong positive opinion, right? So his strong positive opinion kind of on the first iteration propagated to this guy. Now, on the second iteration, again, we take these opinions that happened after the first round of discussions. Again, some discussions happening, reweighting, opinions has changed, right? Now the third one also got a little bit of sort of positive opinion on the subject, and the reason that happened is because in the first step, this guy got some positive opinion from this person, right? And so he kind of improved his attitude towards the subject. And on the second step, this guy, because he listened only to this one, picked up a little bit of his positivity, right? Make sense? Okay. All right. Now, the kind of interesting thing, what happens in this particular setup, if you just keep multiplying this matrix, right? You start with this vector and just keep multiplying by this matrix, and you just keep doing it, right? Which means updating of opinion. So it's like rounds of negotiations, 1 round, 2 rounds, 3 rounds, 4 rounds. You know, they just keep changing and adjusting the opinions. Eventually, let's say, and it actually happens even sooner, but you know, I say like 20 times, right? P20 is P19 times T again, and guess what? They all converge to the same opinion, right? So they started with very different opinions on the subject. The first, second, third guy, eventually they have the same opinion. Now, it took some time. And so the question that the root posed was, well, first of all, is it always going to happen, right? If you start this way, would always committee reach an opinion? And that's actually a very interesting question, because if you know the roles within the committee, and if you know how people sort of listen to other people, you can actually predict if this committee or organization can ever reach consensus, right, on topics. So, you know, with 3 people, maybe it's not so interesting, but if you have, I don't know, United Nations or something, or some like quite big organization, and you know the way people interact and listen to each other, like countries, you know, follow opinions of other countries, right? Some countries follow Russian opinions, some countries follow US opinions quite strongly, right? But nobody really cares what Botswana think. And you can actually predict on a lot of topics what, after some negotiation, what the outcome would be. So, in this case, you know, it works. And the other question would be, of course, how many iterations it needs. Then, you know, what the opinion would be, and who is the opinion leader, right? So whose opinion will affect or influence this decision the most, right? So, and we can actually look into this. It's surprisingly simple but interesting, powerful model. Now, can you think about the situation when this, the consensus will not be reached?
When there is one node which doesn't matter others.
Okay, so one situation is obvious when there is somebody who doesn't care about anybody else, right? He has his opinion and that's it, right? And if nobody can influence him, there is no consensus. That's true. Anything else? Any other situations?
Metrics, so nobody cares at all about another opinions.
Yeah.
So the first opinion will be the same.
Yeah, I mean, or you have a network again where somebody just listens to himself. But there is actually.
Symmetry maybe something.
Yeah, there's a story with actually with not symmetry. Well, it's actually you can think about it a little bit about this a little bit as a symmetry, but with periodicity. If the graph is periodic, here's the picture. Check out this situation. So there is this guy. He is completely not self-confident, right? So his opinion completely. I mean, sorry, this guy's and this guy's. So his opinion completely determined by this guy, right? Whatever this guy says, this says yeah, right? And the same with this. And he is surprisingly also not very confident himself. He just listens to both of his friends, right? So his friends are like ready to follow him, but he listens to them. All right, possible situation, right? Now, when you get like pretty much zero self-confidence in the group of people, consensus most likely will not be reached, which is surprising, right? Because you think the guys are ready to agree on whatever, right? They're completely sort of listening. But let's check it out. This is a matrix, right? 0, 1 half, 1 half, and 1, 0, 0, 1, 0, 0, right? And let's just iterate. Initial belief, right? Take this matrix, multiply it, you get 0, 1, 1. On the next iteration, initial belief, multiply the matrix, get 1, 0, 0. So what's happening with the dynamics in here? Well, it's kind of funny, but yeah, this has an opinion on something. Those guys had probably opposite opinion at the beginning for a second, right? But they listened to, he listens to them, they listen to him. So they flipped their opinions to what this guy thought, but now he was listening to them, to their previous arguments, he changed his opinion based on their arguments. And so this whole thing just keep iterating, iterating, iterating. Obviously, even simple example when there is two nodes and just 1 and 1 will also cause the same situation, right? With two people and each of them trying to be nice and just, and I mean, I'm sure you have seen this when you just try to go like to the movies, which movie to watch, and everybody says, yeah, let's do this, and says, yeah, whatever, and then you just keep going in circles because everybody's trying to be nice. So mathematically, this actually happens because the graph is periodic, right? There's a periodicity in this. There's a cycle of length 2, right? And so it's periodic. Do you know what's periodic, aperiodic? Remember that? Yeah. So this is a periodic graph. Okay, so we know when there is a periodicity in the graph, that's a bad idea, right? So it's clearly is not going to converge, the iterations. So let's actually see when they are going to converge. And it all goes back again to Freeman theorem. I think we talked about it a little bit when we talked about PageRank and eigenvalues, eigenvectors. Just to remind you that if the matrix is a square non-negative matrix, it is irreducible and aperiodic stochastic matrix. Now, in our case, it is a square. It is non-negative by definition because that's the way we define the weights. It's stochastic because it adds up. Every row adds up to 1, and this is actually extremely important because if every row doesn't add up to 1, you don't get this property. It kind of forces normalization. Now, what's irreducible? It means the graph is strongly connected, right? Or you can reach from every node, you can reach every other node. And aperiodic means that the greatest common divisor of the lengths of the cycles is 1, right? Which means you don't have cycles, let's say, of sizes 2, 4, 6, such that each of them can be either, cycles. Each of them can be divided. The lengths can be divided by another, right? Greatest common denominator is different from 1. So in fact, if you have this graph, right? So this is periodicity 2, periodicity 2. Now it's very easy to make this graph aperiodic. How can you do that? With like minor change. You need to make sure you need to add a loop of length 1, right? Because the moment you add a loop of length 1, you break periodicity because now you have a loop of length 1 and you have a loop of length 2, but greatest common divisor will be 1. So what you do is you just add anywhere for any of the nodes, you just add a sort of self loop with a small weight. And so even if you add here, for any of those, you add a self loop with a very, very small weight, this will make this matrix, this graph aperiodic, and the things will converge, right? Okay, so in order for convergence to happen, Freeman's theorem says that if it is non-negative, if it's reducible and aperiodic, then there exists a limit to this type of iterations. So when you take matrix and start putting it into the power, and take the power to infinity, which means you do those iterations, multiple iterations, the matrix will converge. And we'll see in a second what it looks like. Notice here is ij and here is only j index, which really means that the matrix, of course, it remains a matrix, but what it really means is that the rows in this matrix will be identical. You will see in a second. It's kind of surprising. It's a very simple fact. But if you take MATLAB and take a matrix which is non-negative, right, which is irreducible, each is aperiodic, and you just start multiplying it by itself, you'll be very surprised, but you will see that eventually it just all the rows will become equal. It looks like a magic, but that's the theorem. And what it's going to converge to is actually a left eigenvalue of the matrix. I'm sorry, left eigenvector. I mean, well, it's left eigenvalue, left eigenvector, right? Left eigenvector, left eigenvector corresponding to eigenvalue equal to 1. Let me show this, right? Let me actually explain a little bit and show like experiment, but you can actually try it. So the idea is that, again, P of t, like we described this iterations, it was matrix time P of t minus 1. If I do sort of 2 iterations of this process, right, it is t, it's multiplying by t again here. So it's t squared p t minus 2, etc., etc. So if I want to do multiple iterations, this is t to this power times initial story. Now, if we believe the theorem, right, and this is a theorem, so there is a proof there, and look what happens. If you take this matrix and put it into the power t, the theorem says you're going to get identical rows in this matrix, right, and the limit. Now, if that's the case, so the matrix becomes matrix with identical rows, then you multiply it by initial beliefs. Since every row is the same, of course, the product, it doesn't matter what initial beliefs are, the final beliefs will be the same, right? So, what we're trying to say is the following. So if your network satisfies Perron-Frobenius theorem, then when you do multiple iterations, eventually you will converge to identical values of the final beliefs. And those values could actually be found without doing those iterations, but just like by solving left eigenvalue eigenvector problem. Right? And remember, so the matrix is not symmetric, so there is a difference between right eigenvalues and left eigenvalues. So this is left. Okay. An example. You don't believe me? Try it. Put it in MATLAB or whatever. Take this matrix, and this is the matrix we started with. Put it in, like, I don't know, 20th power. You can actually put even in less power than 20th. I think like power 10 will also do the trick. Which means you just multiply it many times so itself for you. That's what you're going to get. So every row will be the same. So, yeah, obviously, if it is the case, you start initial belief, you get sort of final result. There's no questions about it. Now, what's interesting is these values, right? The values that the matrix converges to, that every row converges to, is, of course, the values in the first left eigenvector, right? That corresponds to eigenvalue 1. So what you can do, right, to solve this type of problem, you take your matrix, you solve eigenvalue problem, you find the first left eigenvector, put it in the row of the matrix, and that's what would be if you take this matrix and take to infinite power. And if that's the case, then you multiply your initial beliefs by those numbers, and you get your final beliefs. Right? So now we know how, without doing iterations, and we know how, without looking at, without sort of trying different things, how to actually see, first of all, if the final beliefs exist, right? If they converge there, and we know what the values are. Now the question is, I also promised you that by looking at this, at the matrix, we could actually figure out the influence, right? So the influence in a sense, whose opinion will, influence the result the most. How can we do that?
We can simulate if it's a small matrix.
No, I mean, look, if you look at these numbers, these are actually the weights of different people, right? The weights of their opinion in the final opinion, right? So this is the final opinion, the consensus. And these are of their initial opinions, and that's really the contributions of their initial opinions in the final opinion, right? Because you just take this multiplied by this, plus this multiplied by this, plus this multiplied by that, right? So these numbers are actually telling you the influence of each person in the system. Like the influence in the sense like how his opinion, how important is his opinion in the final opinion. Okay?
Excuse me, would you just sum of columns in the static matrix? It would be have the same value because the last two columns in the static matrix, no, in the static matrix have the same values. Is this just linear?
Oh, is it coincidence? Yeah. So what the key here is, what you need to have is that this all adds up to 1, right? So it's going to be stochastic. Here, it doesn't matter.
It's not always the maximum column would be maximal is resulted.
No, I don't think so. So let's look at this one more time. So limiting belief. So P infinity is you just multiply this final matrix by the original weights, and the weights in this eigenvector, right? This is the coefficients of the original opinions and their contribution to final opinion. So, okay, so it's sort of clear, right? So when you have a system where you don't have which is aperiodic, right? So there is no sort of loops, right? There is no cycles that with the greatest common denominator out except 1, and it is strongly connected, and the strongly connected really means that everybody listens, so you can reach any node from any other node, right? So it means everybody listens to somebody else except not only to himself, right? Literally. And so it kind of avoids a situation where you have like nodes just listening to themselves. In that case, the consensus could be reached, and we can find out what the consensus is, and we can actually calculate the importance of the roles of every person in this final decision. Now, of course, most of the graph, there will be a lot of graphs where that's not those conditions, the Perron-Fabinho theorem is not satisfied. You can actually go a little bit deeper into this and try to see, okay, look, you can say that when Perron-Fabinho's theorem is satisfied, we know what's going to happen, consensus is going to be reached. Now, when it's not satisfied, can we actually look a little deeper and see what options exist there? Can we actually say something beyond that? There's not going to be consensus. Well, one of the sort of more fine points here is based on what's called closed sets. And the set of nodes called closed set if there is no direct link from the node in that set to the node outside the set. So there is no I within the set such that, and j outside of the set such that Tij is greater than 0, right? So there is no direct link from the node in set to the node outside of the set. That's called closed sets. If we look at this graph, do we see closed sets here? Which one?
Node 1.
Node 1, right? Because no direct link from the node to the node outside. So this is a guy, this is one guy, and this is a guy at this situation when he doesn't listen to anybody's opinion, right? 3, 5, and 4, right? This is not a closed set, so nothing goes outside of these guys. Okay? Anything else? Probably not, right? Okay, so these are two closed sets.
Actually, if you add 6 to 4, 3, 5, it also satisfies.
6 to, yeah, you're right. If you take 6, 4, 3, 5, right? Yep, you're right. Yeah, you're right. This is a big closed set, right? Good. Okay. So there is sort of extension to the Freeman theorem that says that that the matrix is convergent if every set of nodes that is strongly connected and closed is aperiodic, right? So it's again the same idea that if you have a closed set now, it is strongly connected, and it's connected and closed is aperiodic, right? So strongly connected and closed is aperiodic. Notice the problem. So this guy is good. The problem with this set, with this one, it is not strongly connected, right? Because remember, strongly connected means you can reach from any node, any node. Here you can reach from one, you can always reach itself. Here you cannot reach 6. Now, but this guy, it is strongly connected, you can reach any node from any other node. So, the theorem, this sort of extension says that if you have those closed sets, strongly connected aperiodic, then each of those sets will reach their own consensus as a result of iterations. Okay? So if you run these iterations, this kind of consensus, iterations, then you will get consensus among these guys. They will reach the same values, right? This guy will stay, of course, with his own opinion, and these guys will take opinion somewhere in between those two, right? So the idea is that after iterations, not each and every person will have his own opinion, but this will will preserve his opinion. These guys will reach sort of local consensus, right? And these guys will be somewhere in between. So in some sense, this is a little bit about sort of group formation, right? Where you can actually call coalitions, right? When you see that there's some people within the bigger committee can actually reach consensus, right, on a smaller scale. But the whole thing will not be able to reach consensus. Okay? I guess that's sort of, this is it. I'm just thinking about other examples. Yeah. So, this model has been introduced in 1974, which is long time ago. And since then, there has been a lot of various updates to this model. People were trying to do various modifications to the model. Now, one of them would, for example, if you think about this before I go and explain what's in there, can you think of, how to make this model a little bit more realistic? Sort of, what do we need to add? What's not realistic in this model?
Different weights are not maybe addicted during iteration.
Right. So, what happens? There are a couple of things that are maybe not very realistic. One is that, weights are static, and that means you kind of, once and forever, you sort of have the same level of, belief, trust in another person, right? So you influence the same way by this person. That's one thing. Another possible situation would be, think about this. When you try to discuss things with somebody, right? And there are different opinions in the room. Whose opinion you tend to listen more to? Somebody who has completely opposite opinion? Or somebody whose opinion is somewhat closer to yours? Yeah.
Should it matter? Should it matter for a person if he just takes both of opinions and he decides for himself what to think?
Yeah, but usually you kind of, if you think about it and you start discussing things, you kind of start intuitively, right? It's not a physical process, right? But you kind of intuitively start thinking, kind of getting closer and paying more attention to the people who support you, right? than those who are on the opposite end of the spectrum in terms of their opinion. So you're kind of looking for people to approve what you're saying, right? And so you're internally putting more weight onto the opinions of the people whose opinion closer to yours. I'm not saying.
Maybe you just stick with the people who have different opinions and try to persuade them that your opinion is more right.
Could be. I mean, you can think about any mechanisms. The point is, with this original model, it was a very, very simplified model, right? And the power of that model is that you could actually analytically show and come up with the conditions for the convergence, right? And you can show how it converges, and you can actually just sort of solve it exactly. Now, the second you start putting different parameters or time varying things, you cannot get analytical result. But of course, you can run experiments, numerical experiments. And so one of the examples is time varying update, where your opinion matrix changes with time. So you have your original opinion matrix, and then there is some sort of function that makes you either more self-confident or less self-confident, right? This is self-opinion, right? And this is external opinion. And your confidence with time either grows or decreases, right? Then there is the story of similar belief, where the idea is that if the matrix, the opinion matrix, is actually it changes, and it depends on how close your opinions are, right? So if you're getting closer in terms of opinion with some other person, your weight, the weight is increasing. Now, if you're thinking the opposite, well, you can build your own model and say, hey, if you're getting closer with opinion to the other person, you stop listening to him, right? That's absolutely fine. It's going to be your model. You can try it. And there are other ways, right? Here, and this one, by the way, this one tells you about the closeness of opinion, right? Just pure closeness of opinion. This one says, there is this, if the opinion is less than some number, then there is a weight, and zero otherwise. So this is like just thresholding, which means if somebody's opinion is way far away from yours, you're just completely ignoring this person, right? That's also an option. Think about political parties, right? Democrats, Republicans, some of them just don't listen to each other at all, or somebody else's opinion doesn't really matter. Okay, so these are all kind of model extensions, and you can think about many more model extensions to this. If you're interested in this story, there is sort of original paper. It's actually pretty cool. There is one mistake in that paper, but it was later corrected. And interestingly enough, it was actually correct like 10 years, 8 years, 7 years after the paper was published. And then the story was again sort of recovered and restored and taught again in the papers by Jackson and Golub. So that's it on this topic. What we're going to do is we're going to have a 5 minutes break, 10 minutes break, 10. Okay.
And I have a question about the last model.
Yeah.
If I'm not mistaken, we're talking about trying to get a consensus between people.
Yeah.
If same people with same beliefs will stick to each other, what consensus will have in the end? Because there are people who are thinking one thing, like democratic and other parties, and they will never reach a consensus.
Probably not. Yeah, and that means we're going to be in this type of situation, right, where there'll be a group of people sticking to one belief, and they will reach consensus among them, and there'll be a group of people who reach consensus among them, and it'll be a situation with no consensus overall. Yeah, easily. And again, the thing is, with these models, when the weights were fixed, we could actually, with linear algebra, analyze this. Now, when this thing changes, there is no easy way to analyze it, and so what you really do is you just run simulations, experiments, numerical, and you see what happens. Yeah. Okay, so let's take a 8 minutes break, and we'll restart at 1. First of all, I want to congratulate you that you survived until the last lecture, which is an achievement on its own. and actually even came here. So again, this lecture will be quite short and probably less mathematical than other lectures, but it also gives you a little bit sort of different perspective on simulation and modeling, and kind of touches upon, well, a bit of sort of political problems. What's kind of interesting, it's also kind of started, the problem has been formulated many years ago, when it was possible to formulate politically incorrect problems in academia. You know, there was some updates to this problem, to the approach has happened based on networks, but it's also about sort of this the way you work with agent-based modeling and agent-based simulations. So again, like 70s, right? This lecture is based off the famous paper by Thomas Schilling. Do you know who that guy is? Yep, Nobel Prize in Economics, eventually, on dynamic models of segregations. You know, the topic is actually very interesting. It's about, and it started with studying of the segregation in the cities. So when you look at the city, most of the cities in the world, you'll find out that they're quite segregated. Segregated means that people of the same race or color tend to live in the same place, tend to live next to each other, right? And so you have parts of town, in the US, you'll have parts of town that are more white, more black, Hispanic, Asian. And the question is, how does it happen? Like, are we so much racists as people that, we just say, look, my way or highway, right? You are going to live only within the neighborhood of only white people, for example. And the interesting thing is that, according to all the reviews and studies, people in general are quite tolerant. And there is nobody who says, I want to have only, say, people of my type around me. Most of the people are okay with, at least half of the people that surrounds them to be of a different type, right? And different type can be, again, gender, I don't know, the race, whatever. But somehow it happens that the cities get segregated. Not only cities, if you look, say, in Russia, you don't see this a lot, but in the US, for example, if you look at multinational companies, you'll realize that there is very often divisions of the companies, even within the US, that all of a sudden becomes like very, say, Chinese, right? And you get a few Chinese guys and they bring more and more, and it's becoming sort of cliquish Chinese, and then there is groups of the company that is like cliquish Indian, right? And it is very surprising because you would assume, and again, when you talk individually to people, nobody actually forcing this, right? But somehow, during the dynamics, the process with time, that's what happens. And so Thomas Schilling kind of looked at this problem and wanted us to see if there is anything from sort of mathematical point of view, from possible to find out within this situation, right? And there is really no good math in here, in the sense of like differential equations that will solve this problem. It is really more about the simulation process, and the reason for that is this is decision-making process, and it's sort of thresholded. And whenever you have a threshold, meaning, and I'll explain in a second what it means, it's actually very hard to write any equations. So, what do we mean by the aggregation, segregation? Let's say the pattern on the left is integrated pattern, right? And this pattern we call segregated, right? And so we have two type of, say, people or two type of points. Maybe, can you close the window, please? I know it's getting hot, but it's kind of annoying with... Thank you. Okay. So this is an actual snapshots, and I mean from the maps, and you can Google and find them. This is US, and what's color-coded is green are white people, the purple Asian, black is black, and orange Latinos, right? And there are different parts of town. You can actually, if you've been there or not, but you realize that Chicago, for example, there is this very nice part where there's, the white population lives. This is the area where all factories used to be. Miami, that's of course, it's Cuban population. LA, yeah, that's your Beverly Hills and marinas, and this is sort of Latina's world, and this is LA Central, where black people live. So it's very sort of well defined and known in US, but the question is like, is there any, how did it happen, right? Now, of course, we can talk about salaries inequalities, education inequalities, and it all, of course, contributes to this situation. But the question is also why white people tend to group the way they group, and it's actually very, very clear boundaries, right? Here's another example. This is like old news now, but still, 2012, the way US voted for president. Also notice that it's not like we have sort of uniformly or somehow scattered blues and among reds, right? There are districts that are sort of contiguous, which are blues versus reds. And by the way, yes, sometimes they of course coincide with, say, better education or higher salaries, right? So it's California or like New York area. But at the same time, like if you look here, it's Arizona. It's actually not a very rich state, right? Texas here, Florida. So the key, or right here up north, Michigan, the message here is that, again, if you notice, there is like, what this means, the way people vote, it means they live there, right? And so there's political preferences within like pretty large regions. They tend to be similar, right? And probably there are more examples. I just don't have it here. But so let's think about the model that we can put together, right? And this is the model that Schilling proposed. We're going to consider population consisting of two types of agents. Agents type A and agents types B. And again, his original study was agents reside in the cells of the grid, two-dimensional geography, 8 neighbors. I call it like sort of dacha kind of thing, right? Where you have a neighbor to up and down, left and right, there's neighbors. Now, some cells do contain agents. Others are empty and are vacant, so you can take them. And every agent kind of evaluates his level of satisfaction with the surrounding. And if he is satisfied, he stays. If he is not satisfied, and there is place to move, he moves. Okay? Now, what defines satisfaction? Well, satisfaction is defined by the number of different type of his neighbors. So let's say you take your neighborhood and you count how many, and it's in this case it's your 8 neighbors, right? And you just count how many of your type of people are your neighbors, right? And if that exceeds your threshold, you're a happy camper, right? You stay. And if, for example, it is below your threshold, you move. Okay? And then this game continues until it reaches certain equilibrium. And the equilibrium could be of 2 types, right? It could be that we reach a happy society where everyone is satisfied, right? Or we have some number of unhappy people simply because they don't have a right empty spot to move to that will satisfy their criteria. Okay? Now, if a person is completely tolerant, so it doesn't, his threshold for people of other type in his neighborhood is 100%, I don't care, right? Then the population is happy, nothing happens. But if not, then there are some people that are there are satisfied and others not, and there's a dynamics. So if we look at this picture, for example, let's say this agent right here, agent X, his preference threshold is 3/7, so he wants 3 out of 7 of his neighbors be of his type. And right now he has 1, 2, 3 out of 7s. He wants, at least 3 7s, right? So if he wants at least 3 out of 7 of his neighbors be of his type. If there are more, that's fine. But if there are less, he's not satisfied. So that's the threshold for him. So this picture is he's a happy agent. He's not doing anything. In this picture, he's unsatisfied because out of his 7 neighbors, and this is the empty cell, right? So there are 7 neighbors. Only 2 are of his type. And within this model, he will move. Now, where will he move? Can he move here? No, because that's, again, will make him unsatisfied agent. Well, unless, of course, there is more like red, living here, there is continuation of this picture. But within this particular picture, no, he'll not move here, so he'll just stuck there being unsatisfied. Okay? That's the model. Now, this is actually original picture from Schilling's paper, where he did this type of simulations by pen and pencil, no computers. He started with this type of configuration, where 2 types of people, the dots and that sign. And after some number of iterations of this game, and empty spots, that's available spots, right? After some iterations of this game, that's what he ended up seeing. So, and I don't actually remember what was the threshold level in this scenario, but we're going to see threshold levels on the next slide. What's interesting, notice that it started pretty kind of randomly, right? But after a while, you get very, very clear groupings and boundaries. Okay? So, formally, the way the model is going to, what the model is going to look like. So we have n nodes, right, and cells where nodes can reside, and we'll have theta as a fraction of occupied nodes by either A or B types. And so number of A type of people plus number of B type of people, there we go, right? Total number of cells times a fraction of occupied. Now, we're going to count the proportion of unlike nearest neighbors for a person, right, for a cell. And this proportion is just, number of unlike nearest neighbors divided by the number of nearest neighbors, right, that are occupied. Well, you saw it on that picture. And then there's utility function we're going to introduce, and the tolerance threshold. And then if the number of unlike nearest neighbors is less than threshold, then it is a satisfied agent. And if it is greater, then it is not satisfied. And so satisfaction is binary 1 or 0. And in general, if you want to measure the satisfaction of the entire society, you just add up satisfaction of every person, right? And eventually, what you want is the sum of this to be maximum, right? That means you get like as happy society as possible, right? And if it is equal NA plus NB, then it's just like everybody's happy. And so every node moves to maximize its utility. And you notice, by the way, that this is this last 2 lectures, we're kind of playing on the boundary in between this computer science, social science, economics. So we're talking about utility functions and maximizing utilities. Okay, so here is a simulation from those guys. This is a starting situation, vacancy 5%, tolerance is 0.5, so it is 50%, which means I'm quite tolerant. I'm happy to have 50% of the people around me being of not my type. right? I mean, it's quite tolerant. What happens? After a few iterations, you get those. After a few more iterations, that. After 400 iterations, that's what you got. White dots, these are the salt. It's like empty spots, right, where the people can move. And with a tolerance of 50%, you get complete segregation, which is extremely surprising, right? Because you would expect that with that level of tolerance, the population will remain mixed. But in fact, it got completely segregated. Now, to measure, of course, we want to be a little bit more precise. We want to measure the level of segregation. We're going to introduce a few metrics later on the slides. But the point, of course, is if you take one particular pixel and you look at the neighbors, right? And if they're of the same type, of course, you're segregated, right? And if they're different, you're not segregated. So you can calculate, for example, the boundaries, right? And of course, the total length of a boundary is here much more than here, right? Because over here it's only the guys that are along the boundaries that have neighbors of a different type, right? And here, like pretty much everybody have a neighbor of a different type. So slightly different simulations. Again, different levels of filling factors, right? And different threshold parameters, causes very, very different behaviors. So what the algorithm is? We go through time steps, and in some way it is quite similar to what we've done. Remember we talked about, well, some of you who were here when we talked about infection propagation, right? We talked about two approaches. We talked about differential equations, and we also talked about simulations, where you can actually simulate the agents moving on the network. And so this is the same story. We're going to try to simulate this. So what we do is we go through all the time steps, and at every time step we select an agent. So select a cell with an agent. If the utility is 0, which means he's unhappy agent, we're going to move to an empty location to maximize utility, right? So we're going to move to empty location where utility is higher than 0, which is in our case is 1. And we can either sort of randomly select out of available locations where to move, or there are different sort of scenarios where, for example, can move to a nearest available location, right? Interestingly enough, it doesn't really matter. You do this or you do that. Eventually, it's going to segregate. It's just sort of the speed with which the segregation happens changes. And so you just repeat doing it until you either utilities are maximized, right? Which means you get a happy world. This is the total number of people of both types, and this is the sum of utilities. It has to be equal if everybody is happy. Or we reach some sort of frozen state when you cannot move anymore because there is no place to move, right? You're not happy, but any other location you try to go to, you will still be unhappy, right? And then the sum of utilities is less, and the total utility of the society is that. Now, if you think about this, the dynamics here comes from the fact that you might not be interested in moving yourself on the first iteration, right? Because you're quite happy with your neighborhood. But then one of your neighbors, by whatever reason, because he was not happy, moves, right? And then all of a sudden, your neighborhood changed, and then the person of another type moves in your neighborhood. Then you're kind of getting concerned, but then if one other neighbor moves out and somebody else moves in, you're getting like really concerned, then you move out. In fact, that's, again, for maybe for Russia, for Moscow, it's not so obvious, but say if like in San Francisco, it is very absolutely like you could see this like literally happening within like 5 to 7 years, like parts of the town, of the city that were originally black being replaced by Chinese, right? Where there's 1 family, 2 families, 3 families, and then people start moving out and they start moving in. and all of a sudden, 5 years later, the entire neighborhood is completely changed, right, by those type of relocation. So it is quite sort of, the model is quite natural in a sense. I mean, you see this happening. Now, of course, this is again very, very simplistic and basic model. Remember, it's done in 70s, so no computing power. Whatever he could do, he did. Today, if you want to reproduce this, of course, you can make it much more interesting, which is you can take people not necessarily on the grid, but you can have them, however else located on the network, right? You can actually, for every person, you can have very different thresholds, right? And you can do many, many more things. You can put much, much more complicated rules and simulate this scenarios. But again, the basic, the most fundamental, this is where it comes from. And then the question is, how do we measure segregation? As I mentioned, well, you can think about different segregation indices. So the Freeman segregation index tells us this E star is observed proportion of what you try to do is you think about the proportion of the ties between groups. So this is the boundaries, literally, right? Normalized by expected proportion of random ties in this situation. So literally, if you don't have if your proportion of between group ties is very low, right, then your segregation index is high. Otherwise, it is low. Or shooting solid mixing index. This is again number of, remember, the P is where is it? It's proportion of unlike nearest neighbors, right? And what you're saying is mixing index is just proportion of unlike your nearest neighbors, just normalized, right? And if this is high, then it mixed well because you have a lot of unlike your nearest neighbors. And if this is low, this number is low, you have very few. So this is mixing index. We can actually also measure, if you want, using assortative mixing, the same one that we talked about, remember, many times, when we talked about clustering. The idea is also very similar, right? You can actually, this index counts, when you talk about clustering, it counts the sort of the ratio of internal connections within the cluster versus overall connections. So it's all sort of the same ideas. But, slightly different metrics, but they all tries to understand, the boundaries, right, and how things are mixed, who's your neighbors. So we can focus on this, on mixing index again. If it is high, we're in a mixed society. If it is low, right, which means the proportion of unlike your people is low, we're in a segregated world. Now, how is it connected to networks? Well, sort of obviously, the connection is obvious. This is the world that Schilling looked into. If you think about network, well, that's your representation as a network, right? You just have, for every node, you have like nearest neighbors connections, 8 connections. But again, if you start modeling this with a network, then you are free to, put any geometry of the network in place, right? So not necessarily just sort of the neighbors and touch a kind of situation. In fact, there has been quite a few numerical experiments, and again, notice the original paper is 1970s, right? So I think this is one of the first papers that started doing numerical experiments of this type of model on networks, right? 2010, and here you have a regular graph. You have your random network, geometric random network, the scale-free network, and the sort of fractals, which somewhat representative for the way things are organized in corporations. So these are pretty much the same network type. It's just here it's shown with some restriction on edges, so there's more kind of edges here. Now, if you think about this particular model right now, and the rules that we just described, where do you think, on which networks do you think you will see largest segregation? Because obviously now a network will also affect, right? Before we had only these threshold parameters, now we also have the network. So which one do you think is more prone to segregation under all other conditions being the same? Where do you think segregation will happen easier?
I think on the scale-free network, because it has a lot of clusters.
Okay, could be. Any other opinion?
Let's say fractal. I don't know why.
Okay, it feels like it. All right, well, let's see what actually, I mean, again, the thing is, the second you step out from various, and you keep seeing this over and over again. The moment you step away from a very simple model, all of a sudden, there is no, exact analytical solution, and then you pretty much start doing experimentations and modeling. And so, what you just telling me, guys, is somewhat intuition, right? It's intuitive. I cannot prove or disprove, right? There is no sort of correct answer in terms of like, okay, well, there is this theorem, right, that tells you that. But based on the simulations, that's the results. And if you notice, can you see anything here? Well, sort of. So this one is way segregated, right? So you're right that fractals are extremely segregated. So this is corporate culture. Geometric also got pretty strong segregation. In fact, this one, you got groups here that are segregated. So, but it's slightly different right now. This regular one got completely segregated, right? With a big cluster. So in fact, the sort of regular lattice and fractals is probably the worst in terms of segregation. And this is geometric, and that's how we live, right? This is how we work. So in some sense, from the point of view of this network and studies, we kind of live and work in the worst, in the most sort of susceptible to segregation geometries, right? Here is sort of surprising results of all these experiments. Now, first of all, yes, you can actually, we looked at the pictures, but you can also actually count that segregation index, right, mixing index. And so this is the difference between grid, random, scale-free, and the Sierpinski. This is the fractals. You can look at them, but what's interesting is, and notice this is mixity, right? So how the population is mixed, which means when it is low, we have high segregation, right? When it is high, it's good. Now, this is our tolerance. So what happens at this end? We have actually a very good mixity. Why is it so high at this end?
Maybe people keep moving?
Because tolerance is very low, right? Tolerance is very low, so it's actually very, very much mixed up society, so nobody cares. Nobody moves. It's actually Berkeley in California. That's sort of the way things are. It's a complete mixture of all different cultures. Nobody cares. What about this one?
Everybody's happy.
It's actually most likely,
Keep it moving.
okay. So this one is everybody is happy, right? And nobody moves because the tolerance is low. Tolerance is high, right? So, no. It's the other way around, right? Here is tolerance is high. This is, sorry guys, I point to the wrong spot. Tolerance is high, right? So you're happy, you're not moving anywhere, right? This is the happy world scenario. You don't care, you just sit there. Now, this is tolerance is low, right? Which means you're almost always unhappy, right? And that means if you're starting with mixed scenario, you're not just going to go anywhere because there's just no way to go, right? You're randomly, and again, remember it's that experiments where they start with sort of random distribution, right? So you're quite randomly distributed, so you're quite mixed, but you cannot, I mean, you're in a very unhappy world, right? Because you just don't have place to move.
You just hate all your neighbors.
You hate all your neighbors, and the entire country hates, everybody, and that's sort of your революционная ситуация, да? So that's sort of bad part. This is a happy world, but it's hard to get there. This is a bad part. Now, what's surprising is what you see here. That is the biggest surprise of the model, which is you have the 50% tolerance, which means you're pretty happy with or even like 60% tolerance. So you're happy with 60% of your neighbors being of different type. Each person individually is happy with that. But as a group, right, as a group dynamics, it causes tremendous segregation.
Could you please remind what parameters or characteristics of people or something, or object was considered like?
So in his study, in particular in his study, back in 70s, it was still possible in US talk about race. And so he actually considered, like literally, you can read in his paper, it's about blacks and whites, right? It's about racial segregation. But, you can think about like any factors why you would prefer to live, in a different neighborhood. And I mean, one of the biggest would be, of course, the income, right? Rich people, poor people. And if you notice, it's of course, completely segregated, right? You don't see rich people living among poor people or other way around. And then in Moscow, it's actually, you start seeing this too, right? The segregations, the enclaves of different cultures, enclaves of different people living. And in fact, there are more studies, and one of the sort of factors, one of the sort of conclusions you can get from network study is that there are certain patterns, right, geometrical patterns that can increase the separation, the segregation, or decrease it. Like for example, putting, of course, and some of them are obvious, right? Putting freeways will increase the segregation simply because you're artificially cutting out communication between parts of town. I mean, even if you live around here, you will notice that there are very different people who live on this side of Leningradsky Prospect and that side of Leningradsky Prospect. There is no easy crossing. Or that live on a different side of Begovaya Street. Which is third ring, right? You cannot cross it easily there, and there is different local subcultures that exist there. So it's it's noticeable even here. And if you notice here, for example, on the grid, there is still like larger mixity, right? So the larger the better, right? Because mixity means opposite to segregation, right? So here the worst behavior is on fractals, right? So when you have this sort of completely hierarchical structure, that causes the most segregation. But this is obviously, it's not about the way people live. It's about people work, right? Because you have this pure hierarchical structure. But what's interesting is, again, here is a scale tree. Here is this one is a grid, and so in some sense, grid is gives us the highest out of those. Gives us the highest mixity. Anyway, I would say the striking conclusion is right here, right? This area, and it is. That's why the paper became famous, because nobody expected that there is a sort of. It's really not the people, not each and every person. It is the sort of the group dynamics that causes this. And it actually part of this, part of why he got Nobel Prize eventually, it's this micro motives, macro behaviors, right? So micro motives means motives of each individual agent, each individual person, right? And how slight changes in those micro motives cause dramatic changes in macroscopic behavior. Because if you notice, slight change from, let's say, 60 to 70%, acceptance or tolerance, right, changes from very little mixity to high mixity, right? And so that is sort of what made the paper famous. And I mean, this is like, of course, this is latest simulations, but it's kind of the conclusion. It kind of confirms the conclusion of his paper, right? And that the fact that yes, different network, yes, do exhibit different behavior, but they still have overall similar pattern, which is deep in the middle. Yeah, and then there is, of course, guys did some different, different modeling. Again, now when you have computers, you can actually add a little bit of randomness, right? Don't make the rules, exact, precise. Just add some noise, right? So you kind of, yeah, I have a threshold, but maybe I'll move, maybe not, and so you can avoid those freezing situation, right? The situation when you don't have a place to move because you can still move, saying, yeah, I mean, I'm not the new location does not satisfy me, but I'll still move there. It's, maybe you heard about optimization. Optimization criteria is called simulated annealing. The process, okay. Well, the idea is when you try to optimize a function, you don't always go greedy, sort of downhill, downhill, downhill. Sometimes you allow it to make uphill steps such a way that eventually you might find the global minimum. And so that's the same idea. You sometimes allow it to move, though the new location it does make you happier, but you still move there. So the things like keep moving with a little bit of probability. And so they tried this. It changes things a little bit, but not dramatically. So I guess the main conclusion here is that spatial segregation taking place even though no individual agent is actively seeking it, right? So every person is quite tolerant. Nobody actually seeks for the segregation, but it actually, as a group dynamic, it happens. A network, does affect this. So that's kind of the outcome of all the studies. Again, if you're interested, this is the original paper, and there is some more recent sort of experimentation and research on this topic. Okay, done with that. Now, we're pretty much done. What did we do this module? We talked about link prediction. What was that about? Who remembers?
We tried to predict whether there is a link between two nodes in the graph.
And how did we do that?
So we can use information about the graph, so we can just divide our. So we just seek all the pairs of the nodes, so we know whether they have between them links or not. So we just divide them and train test split and just train a classification problem.
Yeah. So we try to look for different features that will tell you that there is a chance that two nodes are connected, right? And then we can either just say go through all the possible pairs and rank them by those features. Or we can actually set it up as a machine learning problem, right, and try to predict the existence based and train on training classifier on existing links. Now, the naive question here is, what was one of the strongest features in social networks that predict the existence of the link between two people? Oh, come on.
Maybe common names.
What? No. Remember your Facebook or I don't know. They give you a suggestion for people.
The place of the work, the place where you stand.
Common friends, right? The number of common friends, right? This is the strongest feature. Okay, label propagational graph. What that is about? Exam is coming. So what was that about? You have some nodes with labels. You have other nodes with no labels. So you want to propagate to the nodes where you don't have the labels, information from the nodes that do have labels. So it is a classification problem, right? In the sense of, you have labels, right? Sort of binary or whatever categorical variables. Categorical values, or you might think about it as a regression problem where you have values at certain nodes and you spread them around. Again, the daily example would be the person doesn't show his age on Facebook, right? How do you find it out? How do you predict that age? Well, yeah, you look at the ages of the neighbors, right, of his friends. Eventually, they are correlated, right? This works only when the information on the nodes are correlated. And when we talked about this, we talked about like the simplest things, which is like literally, as I described, look at their nearest nodes and try to average information or somehow propagate it to more sort of techie methods, more mathematical methods where we talked about like semi-supervised learning and optimizing some functionals, etc., etc. Now, epidemics on networks. What's that?
Spreading of epidemics in 3 models.
Okay, what kind of models are there?
So at one point we know that if the man is ill, he can't be cured, so he's like walking dead.
So what's the name of the model? So there's SI model, susceptible infected.
There are also the possibility that this guy will be just cured. So it's another model. So it's susceptible SI.
Okay, so there are SI, there is SIS, and there is SIR models, right? 3 types of models. The SI model goes from susceptible to infected and then stays infected. And in that model, if you have a connected graph, everybody gets infected, right? Because there's no way out of it. It just takes different amount of time. Now then there is SIS model when it's susceptible infected and then recovers and can again get infected. You get a flu, you recover, you can get a flu again. And in that type of model, you might get some group of nodes, some percentile of people always sick, but it will be different people with time. But the sort of flu kind of moves around, right? There are groups of people that are sick, then they recover, but other people get sick, right? It's just you preserve the sort of the ratio of the sick people. And then the third one is SIR model, which is susceptible, infected, and then recovered or removed, in the sense that either the person dies or he's recovered and he got immune to the disease, and so he'll never get infected again. And in all those models, there's really a critical parameter that controls the behavior, that kind of differentiates the situation when you get an epidemics, which is like lots of people, almost all people get sick, versus the situation where your disease just dies out and there's a few people get sick, but not the entire population. So what's that parameter? Do you remember? Those who hasn't been on the lecture didn't even read the lecture. Okay, got it. So the parameter is the ratio of what? It says recovery rate versus infection rate. So when in a world where everybody talks to everybody, it's the ratio of infection rate to recovery rate, or recovery rate to infection rate. So in a situation when you don't have a graph and you have a situation where every person communicates with any other person, or interacts with any other person, which is kind of called full mixing scenario, the threshold for this ratio is 1, which is literally if infection rate exceeds recovery rate, eventually everybody got sick. If infection rate is below recovery rate, very quickly everybody gets recovered and the disease dies out. Now, if you have a network, that threshold, this ratio, you compare not to 1 anymore, the threshold becomes 1 over lambda 1, which is lambda is an eigenvalue of the graph. And it actually encodes the structure of the graph. And so then it changes. And some graphs, the same way as what we saw here in the spatial segregation story, some graphs are more susceptible to infection propagation, and others kind of more resistant to infection propagation, okay? Depending on graph structure. For example, if you compare regular grid and small world network, where do you think infection spreads easier and faster? Small world, right? Why?
Because it's like the diameter is less, so
Yeah.
it's connected to
because you have like this long distance connections, right, which instantly takes you infection from your local neighborhood to like global scales. And in fact, you can instantly think about, again, like sort of real life application is, your airlines, right? That's why when you have an outbreak of disease somewhere, the first thing need to be controlled is long distance travel, right? I mean, obvious thing, but that's sort of that model tells you also that that's the way things are. Now, what about this diffusion of innovation, influence maximization? What's that story?
It's about acceptance of, for example, new technologies based on how many friends of mine have accepted.
Right. So this is it's sort of threshold-based decision-making process, right, where you can make where you decide on what to do based on your friends. Now, there are a couple of things I want to emphasize here. One, it is this process of decision making is very different from this epidemics on networks, because when you look at the epidemics on networks, where flu doesn't care, it doesn't ask you, do you want to get the flu, right? You just get it because of the way, because of your connections. And if some number of your friends are sick, there's a good probability you're going to get sick because of that. Now, with this diffusion of innovation, it is a situation when you are, as an active agent, are making decision. For example, you can switch from one mobile operator to another depending on how many friends of yours are on that operator, because for you there is economic incentives of doing so. So it's conscious, economically based, utility-based decision you make. And it is also threshold model in a sense, the way we considered it, in a sense that you don't do anything unless there is a sort of unless you reach threshold. It's also a model of appraisal and revolution, whatever you call this. If you look at the Facebook and there is some meeting, demonstration, whatever, you look at how many friends of yours is going to go there, right? And for some people it's enough that one person. For some people don't care. For them the threshold level is pretty much zero, so you don't care, you just go, right? Some people will see a couple of their friends go, and they go. Other people will require 70% of their friends before they feel comfortable going there. So in some sense, because of that, say if social media and Facebook, they do act in two ways, right? On one hand, it's information propagation, information spread. On the other hand, it is the influence story, and that's why government is so concerned about the social networks, because they can actually help influence decision making. And the second part, influence maximization, what was that about?
It's about choosing the ones who we want to activate to maximize our
Right. So the idea is that when you have this type of settings and you have some sort of active nodes, right, they can propagate their influence and decision making across the network. And depending on the selection of those nodes, their influence can spread pretty far, right? And the problem is how to find those nodes that will maximize the influence, right? So let's say you run a promotion and you have enough money to give out, 100 iPhones, right, in free plans. Obviously, those people will switch to your mobile operator. So how to select those 100 people such that they will influence by, switching to your network, they will influence their friends to switch there too. Now, it's important here to understand influence. It's not in the sense of convincing somebody, but it is in the sense that those people, for their friends, it will be economically preferable to switch, right? Because the number of their friends with this new network will be higher than with the old one, and so it will be beneficial for them to join that network. And social learning and spatial segregation, we talked about it today. I hope we don't need to repeat that, right? So social learning is about changing an opinion on a graph, right? And how iteratively we can look into this. Opinion changing and spatial segregation, we just talked about it. It's the fact that also within threshold models, with different preferences, you still can get segregation. So if you notice, pretty much this module was a lot about different processes on the networks, and some of those problems can be solved precisely, sort of algorithmically. Some of them actually require numerical simulations in either agent-based modeling or some other approach. And with that we're done.